All right, so here we want to introduce the concept of strong induction. So the idea here is that we have in the previous section this idea of induction. So really we just needed to prove the base case. And then we assumed, right, so we had the base case. And then we assumed for some k, p sub k, to be true. All right, p of 0, right? Not necessarily 0. And then we assumed p of k true. All right. Knowing nothing of the previous term, right? We just said the p sub k was true for all values of k greater than or equal to 0. So that was our just basic induction. All right. Now, the idea behind strong induction, all right, and for basic induction, we use the analogy there of dominoes, right, where we had dominoes lined up, and if we pushed one initially, right, it caused the rest of them to kind of fall down. All right, now for strong induction, what we want to think of instead of these dominoes is this idea almost like a ladder. Right, where if you find yourself here in this step here, you need to know that the other 3 steps are there for you, right? Let's say you're climbing up the ladder. In order to get to the 4th one, you need to know that step 3 was there, step 2 was there, step 1 was there for you as well, right? Now that is kind of the main difference here between strong induction, right? Whereas basic induction, we had you assume p sub k. For strong induction, we assume true for all j less than or equal to k. So if we say p of k is true, so is like p of j minus 1, etc. Okay, and then besides, or not besides, but additionally, we can think of, well, the ladder, not necessarily the next step, but if we wanted to get to step 20, right, and we knew p of 12 was true and p of 8, those were true, right, then we can use those in combination, right, to get us to step 20. Right, so it doesn't necessarily have to be a jump by 1, right, as long as we know the all the cases below that are true. All right, so here's how we go about proving strong induction, right? So here is the approach. Okay, so we assume p of j true. And this will work for all j less than or equal to k. All right. And sorry here, I think here before we get to that, excuse me. Right here, forgot the important part, right? Strong induction. Right, we need our base case. Proof p of 0 is true. And again, sometimes it might be necessary to prove more than one base case, right? But just in general, we have our base case or cases, right? And here is where the inductive step comes into play. Okay. Assume that P of J is true for all J less than or equal to K, and then we prove P of K plus 1 is true. All right. Okay. All right. So now let's take a look at a couple of examples here. All right. So here, let's say I want to prove an n square chocolate bar always takes exactly n minus 1 breaks to reduce to single squares. Okay. All right. So for this one, we need to use strong induction, right? Because if we think of here, so first of all, just kind of to get an idea, assume we have a chocolate bar that is, think of those Hershey's, right? That have those individual squares you can break off, or any piece of chocolate here, right? Assume you have, right, one with just divided in half, right? And if you break it along here, right, you take one break to get to two pieces. Two pieces. All right, so here in this case, n is 2, right? And then n minus 1 gives me 1 break. And then here, let's think of here. All right, now the reason we need strong induction here is of how we make the breaks, right? The breaks, as we can see here, don't always cut the chocolate in half. All right, if we look here, we have our first break. So leads us to 2 pieces, right? But those pieces are not equivalent here, so we could keep going here. And we have a second break here. And now we have here 2 breaks, right? N is equal to 3 pieces, and we see that it took 2 breaks. All right. All right, and we need strong induction because if we think of just a bigger chocolate bar here, let's say we make our first break here. We just break off this piece in the corner. All right, and that would be 1 break here. And then we're left with 2 pieces. All right, here, but then this one is a single square. Another one clearly is not a single square, right? So what we need is, if I call this piece A and this piece B, right, I need A, the total of A plus B, and whatever size I decide to break these off, right? A plus B to be equal to, excuse me, N plus 1 here, right, for my inductive hypothesis, right? So here, the inductive hypotheses must imply to both A and B, right? Not just Rn. All right, so let's just keep that in mind here. Okay? All right. Okay. Okay. So let's start here with our proof here. All right, so here we'll let P sub n be the statement. It takes n minus 1 breaks to reduce an n square bar to single squares. All right, so our base case here starts at 2. All right, 1 squared, no breaks required. It's a single square already. So we'll start with the base case of 2, which we illustrated previously, right, in our first kind of illustration here. All right, so here it looks like this. All right, and we saw 2 minus 1 equals 1 break. That checks out. Okay, so now here is my inductive case. All right, here I'm gonna fix k to be greater than or equal to 2. All right, and I assume P of j for all j less than or equal to k to be true. All right. Okay. So now we want to consider a k plus 1 square bar. Okay, so we increase it by a size of 1. So let's say I make 1 break. All right, and again, just the general break doesn't necessarily have to be 2 even pieces. All right, I just want to say that 1 break, and that produces 2 bars of size a squares and b squares. Okay. All right, now clearly here, a less than or equal to k and b less than or equal to k. All right. We can take it to the extreme where we just break off, if it's k plus 1 squares, and we could break off just a single square, right? Then one of them would be 1 and the other one would be k. Okay? All right, so that means that they follow my inductive step, right? I assume P of j, so that falls in line with P of j. All right, so by the inductive hypothesis, right. All right, by the inductive hypothesis, the A bar takes A minus 1 breaks, and the B bar takes B minus 1 breaks. All right, and another thing, A plus B together equals to K plus 1. All right. Okay. So putting that together here, right, so we have a total of 1 plus A minus 1 plus B minus 1, which equals to A plus B minus 1, which A plus B is K plus 1, minus 1, so we get K minus 1. Excuse me, K breaks. All right. So P of K plus 1 is true. Okay, and by strong induction, P of N holds for all N greater than or equal to 2. All right, and then one more example involving prime factorization. All right, and I want to prove that every integer n greater than or equal to 2 is either prime or a product of primes. Okay. All right. So again, strong induction, because we want at whatever K I am along the way, I want to use the fact that all previous ones follow this are true as well. Okay. So here, the idea here is we have, all right, our base case, right? We have P of 2, right? 2 is prime. So the above is satisfied. Right, now here is my inductive case. And then we fix K to be greater than or equal to 2. All right, and then assume P of J for all J less than or equal to K. All right. So now we go to P of K plus 1. Now there are two cases here, right? Case 1, K plus 1 is prime. So that checks out. All right, so that satisfies the above. All right. Now case 2, K plus 1 is not prime. All right. Well, K plus 1 is right greater than K, right? So what I can do here is, well, if k plus 1 is not prime, it is a composite number, which means k plus 1 is equal to m1 times m2. Right, and clearly both of these, m1 and m2, have to be less than or equal to k, right? So by the inductive hypothesis now, here I can continue with a sort of recursion, right? Here's here more like a proof sketch. From here, we could say, well, I can keep going here and say m1 is prime, m1 is prime. If it's not prime, then I can again rewrite it as a product of primes because it's part of my inductive hypothesis. If it is prime, then we're done. And the same with m2, right? I can continue going here till I can have, right, a product of primes, right? So as a kind of recursively use the hypothesis test, not the inductive hypothesis.